So, first of all, I would like to thank the organizers of this workshop for the invitation and the colleagues in Palermo for their warm hospitality in this beautiful palace. And so, LSST is, without any doubt, a reference facility for astronomy in the next decade. And actually, let me see, okay. Whatever number you select to describe LSST is impressive. And this morning I want to draw your attention on one parameter in particular, which is the attendu, and because this is a parameter which is quite effective in measuring or ranking the power of a survey telescope. The attendu is basically the area of the primary mirror times the subtended solid angle, normally referred to as the field of view. And for LSST, this number, this parameter, has a value that you will never find in any other telescope. The value exceeds 300. And it's important to mention that for a given optical configuration, this parameter is a constant. This means that for a given optical configuration, larger the primary mirror, smaller is the subtended solid angle, smaller is the field of view. And the LSST telescope design is such that it will maximize the field of view at some expenses of the collecting area. Indeed, the primary mirror has an aperture of 8.4 meters, but as you well know, the effective diameter is a bit smaller than 7 meters. And when I start to think about spectroscopic follow-up for LSST, first, I would say, basic question came immediately to my mind, and the question is which spectroscopic follow-up we can conceive for a machine like LSST that has such a, and I would say, embarrassing large attendu value, and also a sensitivity down to the 24th magnitude. And I would say there will be only one instrument that it's still in its design phase and probably will see first light not before 2025, which is the Mauna Kea Spectroscopic Explorer. This will be a refurbishment of the actual CFHT telescope, and it will be a telescope of 10-meter diameter. And again, the optical configuration design of the telescope will be such to maximize the available field of view. And this is the only instrument which will have an attendu value exceeding 100. And so, as a matter of fact, I would say that both the attendu and the sensitivity of LSST are requirements. If you are optimistic, you will define them challenging, but I would say mostly prohibitive to match with current and near future spectrograph. There will be obvious limitation in sky coverage, in sensitivity, in overall statistics. So you will be forced to think in terms of a spectroscopic follow-up of selected targets only. And this selection procedure will be, by definition, a multi-parameter trade-off analysis, both astrophysically and instrumentally. Indeed, from the instrumental point of view, because you have a finite number of detector pixels by definition in any instrument, and also a finite optic size, you will have competition among spectral resolution, simultaneous spectral coverage, and multiplexing. And from the astrophysical point of view, when in defining a survey strategy, you will have obvious competition among depth, signal to noise, number of objects and fields you want to survey, competition with cadence, and so forth. So, in terms of sensitivity, very roughly speaking, if you think of using a 2-4-meter class telescope, you will basically take spectra of objects that will be significantly brighter than 20 in magnitude. While if you are planning of using 8-meter class telescopes, you can think of reaching magnitude of 20 or even fainter. Everything will also depend on the desired spectral resolution, signal to noise, and exposure time. And also for your follow-up, you will need very likely multiple observing modes or multiple spectroscopic configurations, depending on the target, on the environment, and on the science case itself. So, for example, for population studies or for statistical studies, you will like to have a multi-object and or integral field capabilities, while for full diagnostics of pillars, you may prefer to have a single few object spectroscopy, but with a wide or full spectral coverage. And also, you may want to have different multiple spectral resolution. Obviously, all these multiple observing modes are difficult to impossible to fit within a single instrument. So you will have to start to consider different instruments. So I now start to make a census of the spectroscopic capabilities that will be available in the next decade. This list of instruments doesn't pretend to be complete. I tried to select a specialist spectrograph that will be directly available to our community, so mostly at ESO, and, but I will also mention a few other instruments at American telescopes. So let's start inspected which will be the multi-object capabilities starting in 2020 for wide field spectroscopy. At 4-meter class telescope, we will have foremost on Vista and WIV at the William Herschel, WIV obviously to sample only the northern sky. And this spectrograph will have an ATU of about 50 and a multiplexing between 1,000 and 2,000. At 8-meter class telescope, we will have means at the VLT. First light should be in 2020. While foremost and WIV will cover only the optical spectral range, MUNS will cover part of the optical range in the red, starting at 600 and something nanometer, out to the H-band in the spectral coverage will be almost complete at low resolution of a few thousand, but there will be also a couple of higher resolution grating in the I-band, and I don't know if I can point it, and in the H-band, at 10,000 in the I-band and 20,000 in the H-band for detailed chemistry, for example, of stars and stellar populations. The ATMD value for this facility is smaller. Indeed, the field of view of moons will be only 500 square minutes. But, so this is a very effective multi-object for in dense stellar field, and also to measure rather faint targets. I think it's obvious, but it's worth mentioning that in case you will select one of these facilities, and you will use only a fraction of fibers for your science case, it will be very wise to develop in parallel another science case to use the remaining fibers that in many cases could be the majority. Otherwise, it will be not an efficient use of this spectrograph. Another interesting instrumental configuration for some science case is the integral field unit. This is especially interesting for dense stellar fields or extended object, and in particular, I want to highlight here two IFU spectrograph at the VLT that you will know. They are already in operation. MUSE, which works in the optical and as a field of view of 1 square minute, and KMOS, always at the VLT. This is a deployable IFU, 24 mini IFUs of 9 square second each, and that you can distribute over a 50 square minute field of view. And this spectrograph will allow simultaneous spectral coverage, basically of one band IZ, YJ, H, or K at the spectral resolution of 4,000. For many science cases, however, one could be happy with another instrumental configuration, what I call single few object, but with a wide or complete spectral coverage. And at 4-meter class telescope, there will be soon in 2020, hopefully first light, SOX at the NTT, which simultaneously cover the optical and the near-infrared out to the H-band at a spectral resolution of a few thousand. And, but maybe for some science cases, you would like to perform a very high spectral resolution spectroscopy, a shell spectroscopy, at a resolution of 50,000 and higher, and in this case you can have JARPs at the TNG, obviously only to sample the northern sky, and ARP South plus NIRPs that should see first light in 2019 at the ISO 3.6 meter telescope. And this shell spectrograph will simultaneously cover the optical and the near-infrared spectral range. At 10-meter class telescope, you will have a shooter, and which cover the optical and the near-infrared at a spectral resolution of 10,000 or less. I also like to mention IMAX on Magellan, because this is a quite unique combination of medium high spectral resolution and some multi-object. This will cover only the optical spectral range at a spectral resolution of 20,000 with a multiplexing of 15, so 15 objects can be observed simultaneously. And also at 8-meter class telescope, there will be high spectral resolution capability for a shell spectroscopy. At the VLT in particular, UVS and Espresso to cover the optical range, and Cryores Plus to cover the near-infrared. Then, hopefully, starting from 2024, maybe more, this is the aggressive schedule that ISO still maintain, but probably more realistically in 2025, there should be the ELT. The ELT is the project for a 39-meter telescope with a 10 hour-minutes field of view only. That's what I was saying at the beginning. For a given optical configuration, enlarging the primary mirror area means decreasing the field of view. And the ATD for this telescope is 30. And the ELT will have a first generation instrument suite that will include imager and spectrograph with different spatial and spectral resolution in the optical and in the infrared. And the ability, I would say, to observe over a wide range of wavelengths from the optical to the infrared and in different instrumental configuration is definitely a great advantage to exploit the telescope size to the fullest extent. And the roadmap for the commissioning of the first generation instrument at the ELT is the following. The 3 first light instruments have been selected: a near-infrared imager, a near-infrared integral field spectrograph, and a mid-infrared imager and spectrograph. All these 3 instruments will be assisted by adaptive optics, so will provide high spatial resolution imaging and spectroscopy. For some of the spectroscopic follow-up of LSST, the possibility to combine spatial and spectral resolution could be interesting, although, as we all know, LSST will work in C-limited mode, so you will not take full advantage of the high spatial resolution provided by the ELT. And after first light, there will be the commissioning of 2 other first-generation instruments, a high-resolution spectrograph working at 100,000 spectral resolution, simultaneously covering the optical and the near-infrared range, and a multi-object spectrograph also working in the optical and in the near-infrared. And these 2 graph basically showed on the left the first generation instrument in terms of field of view on the y-axis as a function of the spatial resolution on the x-axis, spatial resolution in millisecond, and you see that, only the MOS, the optical MOS and the high-resolution spectrograph are basically working scene-limited. All the other imager and spectrograph will be assisted by adaptive optics. In the graph on the right, you see the spectral resolution of the spectrographs of the instrument, yes, as a function of wavelength. Obviously, here you have the imagers. I don't know if where I am pointing. Okay, here are the spectrograph. So you see that this first generation instrument are covering most of the spectral resolution that you may be interested in. Obviously, the ELT, I would say, cannot be considered really a survey telescope, and there will be a pressure on this telescope that will be amazing, and so it will be an opportunity to do spectroscopic follow-up of very selected targets, especially the faintest one. And this is my last slide. Actually, I had additional thoughts that are essentially additional questions that I wanted to share with you. In a sense, I ask myself whether for LSST spectroscopic follow-up, we really need massive surveys or even more extremely dedicated spectrograph and or telescopes. And I don't know, it will depend also on the final survey strategy of LSST, on the selected science cases, but if any of these questions, the answer to any of these questions will be yes, I would say it's very wise and very necessary to start planning and negotiating telescope observing time for this follow-up. And probably if you are thinking of having new spectrograph or telescope, it's this well in advance means now or perhaps yesterday. And just one other question. At the very beginning, I mentioned the Mauna Kea Explorer spectrograph. I want also just to mention that a couple of years ago, ESO started a feasibility study for a similar facility in the southern hemisphere. And this first feasibility study has been completed, but for the moment the activity are frozen. The new DG decide to stop for the moment further development because of resources problem. Any of this facility will cost 300 million euros, something like that. So ESO is very busy with the ELT, which cost more than 1 billion. So let's see whether in the future there will be a dedicated 10-meter class telescope for surveys at ESO as well. Thank you very much for your attention.
There are questions? Thank you, Liva, for your talk. I was wondering, this is for something, a comment maybe for all of us, and maybe a question to Colin after this talk, that could be important in a preparation of a white paper for LST strategy, to stress the importance to have already planned some follow-up spectroscopy plan, survey, or program in the white paper, if this could be a strong point to be highlighted in a proposal, to have a plan also with synergy with other future instruments like this.
I guess I'd have a little hesitation there, because we don't want to turn the survey into a mechanism for delivering results for other, like, closed organizations. So it's kind of hard to justify spending time on a facility that's serving a wide set of users if part of the program is to specifically help a particular group that has some other ancillary data. So it helps if it's broadly available in the community, but if it's something like, well, we have a survey going on this other telescope, then it's a little hard to balance those two considerations.
I have just following the discussion that Sala started. It is correct, but probably the added value is not the fact that we have the facility, but the fact that we have GTO. And in some cases, these might be useful. In some others, obviously, there is, in any case, a competition. But this can be like the cherry on top of the cake. The science has to be there. The fact that we can also mention the possibility to use other facilities, in my opinion, is never is always something going in the right direction. But I would like to go back to the point raised by Livia that, in my opinion, is the very crucial one. Right now, the two most important instruments for large spectroscopic surveys that are going to be in action or during LSST operations, PFS at Subaru and MSE, are both of them in the Northern Hemisphere. There is nothing in the Southern Hemisphere. And when we say nothing, doesn't mean only ESO. Gemini is the same. There is nothing like that. So the fact that we are going to have two of the ELTs in the Southern Hemisphere doesn't mean that we are going to cope with the challenges that the spectroscopic follow-up of LSST is going to provide. So sooner or later, this is one of the issues that, obviously not today, not tomorrow, is the ESO community, and in particular the Italian one, has to think about, because it's something that we are entirely missing.
Yeah, just to agree with all these points made here is that 2 years ago or so, the U.S. community did a study on basically this problem of, well, what is the sort of inventory of spectroscopic needs that we will have as a result of LSST, and this mostly focused on Milky Way work, didn't go into extragalactic work, and just sort of said, oh, well, we think we'll need, I mean, if we want to follow up Lyria or whatever your favorite tracer is out to whatever distance in the halo, if we want to follow up dwarf galaxies, we can kind of add up the time we would need on telescopes of a given aperture and a given field of view, and you end up with a number which is just completely way beyond anything that we're able to provide right now. In some sense, we got lucky that the 4 meters that the US built were able to be repurposed for surveys. And that helped a lot. So now we have DESI,